In this presentation, we are going to discuss the first part of Chapter 5, Wave, Motions, and Sound, and we will focus in describe the elastic materials and waves. Elastic materials are materials that recover its original shape after a force deforms it. Vibrations are common in many elastic materials, for example, the spring, or also in the strings of a guitar. Also, there are some systems that can vibrate, for example, the pendulum. Also, the pendulum can vibrate. These are some vibrations we can see. There are another vibrations we can hear, for example, the sound. Yes, that vibrations we can hear. However, there are some vibrations that are invisible to the senses. Some of these vibrations involve heat, light, and electricity. Then, what is a vibration? Vibration is basically an oscillation. It's repeating motion that moves back and forth. Then here we had one example of vibrations. We can see this motion is moved back and forth, and this pendulum is moving around some equilibrium position. As this is, and we can see this is moving around this line, and this is called the equilibrium position. Here we had another system. In this case, we had the system of block and spring, and this is also a vibrational motion. And in this case, we can see the block is moving around, the block that is attached to the spring is moving around some equilibrium position back and forth. Then what variables we need to know if we want to describe any vibration? Then the first variable we want to study is the amplitude. The amplitude is the maximum displacement from the equilibrium position. Then we can see here the amplitude, if this is the equilibrium position, is the maximum displacement of the system, is the maximum vibration from the equilibrium position. Then here the amplitude will be this distance. We can see amplitude is a distance. Yes, then will be meters or centimeters or micrometers or feet. Is the amplitude will be in units of distance. And here in the case of the block and spring, then if this is the equilibrium position, then this will be the amplitude, the distance from the equilibrium position to the maximum displacement. Another variable we need to know if we want to describe any vibration is the cycle. What is the cycle? Is a complete vibration. Is when the system moves from one point to another point and back again. And the amplitude in this case will be moved here, then back. Yes, back again to this point. And this is one complete vibration. Yes, it's moving from this point to this point and then back again to the original position. And this is one complete, the cycle is one complete oscillation of what complete vibration. One more variable is the period. Period is a special time. And this is why we had capital T for period. Is the time required for one complete vibration. Then because it's a time, then it can be in the period can be in minutes, can be in seconds, can be in hours. Then this period is just a time. What happens if we want to calculate the time for just one complete vibration? Sometimes It's difficult to take the time just for one vibrations. And if we want more precision in the measure of for one vibration, what we can do is we can measure the time for more than one vibration. Yes, for 5, for 10 vibrations. And then we can divide the total time for example, for 5 vibrations, or for 5 cycles, divide the total time, divide by 5, and then we will get the time just for one cycle. Then this is why if n is the number of cycles or number of oscillations or number of revolutions, this is different ways we can say the same, and t is the number of the time to complete cycles, then we can get the period. We divide this time by the number of cycles. And what we can do is we can measure, for example, the period for this pendulum we had here. Yes, then let's take n equal 5. Then let's take the time for 5 complete cycles. Then what I suggest you, if you had a phone, then just try to take the time for 5 complete cycles using your phone. And we can start here. 1, 2, 3, 4, 5, and we stop the time. Then I did this one for 3 trials for 5 cycles, and I got this time as 11.70 seconds, 11.83 seconds, and 11.69 seconds. And I did for 3 trials. In this way we will have more accuracy in our measurement. And to take the average of the time, we add these numbers and we divide by 3, and I got the average time for 5 complete cycles is 11.74. Then, but I want to calculate the period. What is the time for one complete oscillation for this pendulum? Then what we need to do is we need to divide the average time. Yes, we need to divide. Then if we want to calculate the period, what we need to do is we divide the average time, which is 11.74, which is the time seconds, divided by the number of cycles. In our experiment is 5. Then if we divide these two numbers, then we will have the period. Then the period in this case, if we divide these two numbers, is 2.348 seconds. If just we keep the 4 significant digits we had there. Then this is the time for this pendulum. This is the time for one complete cycle for this pendulum. Is the time for the pendulum to move from this here and back to the original position for one complete cycle. The other variable, then period, yes, the time for one complete cycle. The next is the frequency. Frequency is the variable that tells you how many cycles the system or the system that are vibrating executed for unit time. How many cycles per unit time? Then in this case, if we want to calculate the frequency, then what we can do is we can divide the number of cycles, as we measure, divide by the time. Then this is why the units of frequency can be revolutions per second, yes, because this corresponds to the revolutions or cycles or vibrations. Can be also cycles per second because we had time in the denominator. Can be turns per second and can be revolutions per minute, and sometimes we can write revolutions per minute like that. In some books they wrote like that. But also there is another way we can give the units for frequency, because we know this time corresponds for one cycle. Then you can just write 1/second because we know this corresponds to one cycle. Yes, then the units can be just 1/second, and in some cases we can write this one. Remember, if we move this one to the top, just we change the sign of the exponent, and this is in some books also. You can see the units for frequency is second to the -1 power. And all these are units for frequency. And 1/second has a special name, which is hertz, and the symbol to represent the hertz is H, capital H, and Z. And all these are units for frequency. Then let's now calculate the frequency for this pendulum. And we know in this case the n, the number of cycles, equal 5, and the time for 5 cycles will be 11. Sorry, the time for 5 cycles will be 11.74 seconds. And if we divide these two numbers, we will get 0.4259, 1/second. You can see the second is in the denominator. And we can say the frequency for this pendulum is 0.4259. And we can write 1/second as hertz. Then in 1 second, yes, this pendulum executes about half cycle. Yes, it's 0.4259 hertz, means in the unit time this pendulum executes just about half of the cycle. And if we compare these two equations, this is the equations we use to calculate the period. This is the equation we use to calculate the frequency. And we can see they are inverse. Yes, here we had T/n, and here we had n/t. And we can see the relation between period and frequency is inverse relation. And this is why if we know the period, we can calculate the frequency. We calculate the inverse of the period. And also, if we know the frequency, then we can calculate the period. It's just we calculate the inverse of the frequency. Then just we can try it for frequency. If we know the period, then we can calculate here the frequency. In this case will be 1/period, but the period is 2.348 seconds. And if you divide this, you will get frequency equals to 0.42 hertz. That is the same value we had here. And these are another two variables that we need to know if we want to describe any vibrational motion. And let's now apply some of this concept when we want to calculate what is the frequency of the system, the vibrating system that has a period of 0.5 seconds. And we know the period. Remember, the period is the time for one complete oscillation, and it's 0.5 seconds. Then if we know the period, we know we can calculate the frequency is how many oscillations in the unit time. Yes, how many oscillations in the unit time. Then we can calculate the frequency. Then the period will be equals to 1 over 0.5 seconds. Then the frequency will be 1 over second, or it will be equals to 2 hertz. And for this system, the frequency is 2 hertz, means in 1 second this system complete 2 cycles. Yes, in 1 second is how many cycles per unit time. In this case, the unit time is seconds. Then this system complete 2 cycles in 1 second. This is the frequency, is 2 hertz. Then the motion of a mass on a spring is called the simple harmonic motion. Simple harmonic motion is just a repetitive movement back and forth through an equilibrium or central position. This is, we already discussed that before. Yes. Another characteristic of the simple harmonic motion is the maximum displacement from one side of the equilibrium position is equal to the maximum displacement on the other side of the equilibrium position. And all the systems we already described, they move at simple harmonic motion. We can describe that motion as simple harmonic motion. Then one graph we can use also to describe simple harmonic motion is the displacement versus time graph. Then what we had here is we are able to take a picture of the motion of this spring at different moments. Yes, at different moments. Then if we just put all the pictures together, then what we will see is this graph. Yes, is how this spring is moving back and forth through the time. We will see how this spring, yes, is moving around the equilibrium position through the time. And finally, we will have some graph like that. And why is important this graph, displacement versus time graph for a vibrational motion? Because if we had this graph, we are able to read, for example, the amplitude, what is the maximum displacement from the equilibrium position. If this is the equilibrium position, then this will be the maximum displacement. In other words, this will be the amplitude. Yes, this will be the amplitude. And also this will be the amplitude in the other direction. Also, we can read the period. Period is the time for one complete oscillation. Yes, we need to check what is the time. We start here, we got this one, then one complete oscillation will be from this point to this point. If we know this time, yes, if we are able to read this time in this graph, then we will know the period for one complete oscillation. We will know the period. Yes, it's the time for one complete oscillation. And if we know the period, we know the frequency, because we know the frequency is the inverse of the period. And this is why if we had the graph displacement, we had the displacement versus time graph for any vibrational motion, then we can get this information. Then now, why we study all these variables to describe a vibration? Because a wave is a traveling vibration in a medium. Then wave is just a vibration. One important thing is the wave, which are vibration, travel through the medium, but the medium itself doesn't travel. Yes, doesn't travel. Just what is traveling is the vibration. In this case, we had vibrations in water, as the medium is water in this case. In this case, we had vibrations in air, which can be sound, for example. Then, in this case, the medium is the air. There are different kind of waves. This depends on how the waves traveling in a medium. Then we have two different kind of waves. One is the transverse wave, the other is the longitudinal wave. And let's check this video to know.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels. In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal.
As you watch in the video, there are two different kind of waves. One is longitudinal wave. In this case, the elements of the medium vibrate in direction parallel to the direction of the wave. Then the particles of the spring vibrate in the same direction of the wave. And one example for longitudinal wave is the sound waves. And I want you to remember this one when we study the sound waves. You can see there are some part of the spring where the spring is closer, but there are another portions they are more separate. And we will see similar behavior when the sound wave is traveling in air. The other kind of wave is the transverse wave. In this case, the elements of the medium or the particles of the spring is vibrate in perpendicular in the direction of the wave. And in this case, we can see the particles of the spring, they vibrate in this direction, but the wave is propagate in this direction. Then they are perpendicular. Yes, perpendicular. Now we are going to study the sound waves, and we know sound wave is a longitudinal wave. Then in the same way we observe in case of the spring that there are some part of the spring when the vibration is propagated through the spring, there are some part of the spring that are closer and there are some part of the spring that are more separate. Then the same happens when the sound is traveling through the air. Then there are some parts where the molecules of the air are closer and there are some parts where the molecules of the air are more separate. And these two zones has different name. Then where the molecules of the air are closer is called condensation or compression zone. Then this, because of there are more density of the molecules of the air, then in these regions they have higher pressure. But in the other regions where the molecules of the air are more separate, there is less density and less pressure. Then we can say the sound is a vibrating object that produces condensations and rarefactions regions when this is traveling through the medium. One more thing is the humans, we can we cannot hear all the frequencies. We can hear just a range of frequency. We can hear between 20 Hz and 20,000 Hz. Now, if we apply the concept, if we compare the graph of the amplitude versus time with what we can see happen with the molecules of the air, then what we can say is the regions where had higher pressure, yes, the condensation zones correspond to the maximum amplitude, yes, in a amplitude versus time graph, and the condensation regions correspond to the maximum amplitude. But the rarefactions regions where the pressure is less correspond to the minimum amplitude. Or we can say the amplitude in negative direction respect to the equilibrium position. And this region correspond to the maximum amplitude, and this correspond to the maximum amplitude. But these regions for low pressure or rarefaction zones correspond to the minimum amplitude or the amplitude in negative direction respect to the equilibrium position. Now, we already know some of the variables we need to describe a vibration, means some of the variables we need to know if we want to describe a wave. And let's now describe few more variables that we will need to describe a wave. Then we already know amplitude. Amplitude is the maximum displacement from the equilibrium position. Yes, this is the equilibrium position, is the maximum displacement from the equilibrium position. Now, the wave crest is the maximum displacement from the equilibrium position in positive direction. Yes, this is crest, this is another crest. But the throw is the maximum displacement but in negative direction of the equilibrium position. Then this is the throw, and here we have another throw. And we know the period. Period is the time to complete one cycle. Yes, and if this is time, if we have time in, this is the time in this direction, then we can say the period, we can, if we know this time and we know this time, then we will know what is the time for one complete cycle. Yes, we can subtract this time minus this time, and we will know the period. If we know the period, we know the frequency, because the frequency is the inverse of the period. And we know is how many cycles can execute the system per unit time. Now we had new variable. This is the wavelength. The wavelength is the distance from crest to crest. This is one definition. Or is the distance the wave travels in one period. Then we can say is the distance from crest to crest. Also, we can say is the distance from throw to throw. Yes, this is the distance from here to here, or distance from here to here. But also, the wavelength is the distance that the wave travels in one period. And now we had new variable, and wavelength is a distance. This can be in meters, can be in centimeters, can be in micrometers, can be in feet. And the symbol we use for the wavelength is lambda. It's a Greek letter, and we will use this to represent the wavelength. And in this example, we had two waves. And these two waves, we can see they had different amplitudes. However, we can see the period and the frequency are the same, but they have different amplitudes. Why? Because the distance from the equilibrium positions are different. Yes. And we can say the red one has larger amplitude compared with the blue one. In the second graph, what we had two waves. They had the same amplitude, means the distance from the equilibrium positions are the same. However, the period and the frequency is different. Yes. The blue one has larger period and less frequency. In the second one has short period and larger frequency. Yes, because remember, frequency and period, they are inverse. And we can say the red one has greater frequency compared with the blue one. Now let's try to correlate these three variables. And we want to correlate the wavelength, the period, and the speed of the wave. One important thing is the wave travel at constant speed in a particular medium. Always the wave will travel at constant speed in a particular medium. Then this is important, constant speed. Because the speed is constant, the only equation we need to know to describe the motion of the wave will be velocity equal to distance over time. You can see here we don't have average velocity because or average speed, because this is constant value. This is why we don't have here average. Then now, if we want to describe a wave, then we can take a special distance. We know the velocity is always the same, it's constant. Let's take the special distance. In this case, the distance, we had one special distance is one wavelength. Yes, it's this one. And we know what is the time for this, for one wavelength. Yes, this corresponds to one period. Yes, remember the wavelength is the distance that the wave travel in one period. And this is why we can, for distance, we can say one wavelength divided by one correspond to one period. If we want to write this one using symbols, then we will say wavelength divided by the period. Then let's now write this equation like that. Yes, we just rewrite the equation. You can see these are equivalent equation. If we multiply wavelength times 1, we will get wavelength over time. But we know the inverse of the period is the frequency. Then we can write this one. And this is the equation we had here. Is then the velocity of the wave equals to the wavelength multiplied by the frequency. Also, the velocity of the wave equals to the wavelength divided by the period. And remember, for one wavelength correspond one period. And let's now try to solve this problem. Then we had a sound wave with a frequency of 260 Hertz. In frequency, we had a sound wave. The frequency is 260 Hertz. And the wavelength is 1.27 meters. And what is the speed we expected? Then this is a constant speed, and we applying the equation for for the motion at constant speed, we got this relation. Then because we know the wavelength, we know the frequency, then we can calculate the speed of the sound. Then the wavelength will be 1.27 meters multiplied by the frequency. But we know hertz is 1/second. Then I will write here is 260 1/second. And the units we expected for speed will be meters per second. And you can see meters times 1 will be meters over second. Then we had the correct unit. If we multiply these two numbers, we will get here 330 meters per second. Then the velocity of the sound at this frequency will be 330 meters per second. And let's solve one more problem. And we know the humans, we can hear between 20 hertz in the range of frequency between 20 hertz and 20 kilohertz. But the human ear is more sensitive of the sound at 2500 hertz. And if we assume at this frequency the sound moves at this speed, then we want to know what is the wavelength of this sound. Then let's try to see the information we had. And we had frequency is 2500 hertz. The speed is 330 meters per second. Then we want to calculate the wavelength. Then this is the equation we can use to describe any wave. Yes, any wave. And we know the frequency, we know the speed, no problem with the units because we know hertz means 1/second. Then we can solve for the wavelength when we divide by the frequency on both sides. And we will have the wavelength equals to the velocity or the speed over the frequency. And then will be at 330 meters per second divided by 2500. And let me write 1/second. Just remember hertz is 1/second. And now let's divide these numbers and we will get about point. And let's check the units. We expected meters, yes, meters per second. And now we flip this one. 1/second is in the denominator, then is division. Yes, we need to flip this one. And this cancel out. And finally, we had 0.meters. And if we want to write this one in centimeters, then just we know 1 meters equal to 100 centimeters. Then what we need to do is just we need to multiply by 100. Yes, let me do it here just as example. Sorry, 1 meter. Here we have 100 centimeters. And this cancel out, we have centimeters. If you had to give the answer in centimeters, yes, if you had to give the answer in centimeters, then this is the procedure you had to follow. Then if if the frequency of the sound is 2500 hertz, then the wavelength will be about 0.13 meters, yes, or 13 centimeters. And let's write the results we got from the last two problems. And what we had in both cases, we had sound and we had the same speed. Yes, both cases we had the same speed of the sound. Yes, this is for the first problem. In the second problem, but in the first problem, the frequency of the sound was 260 hertz, and in the second problem, the frequency was 2500 hertz. The wavelength in first case was about 1.27 meters. In the second problem, we got about 0.13 meters. And we can think this is about 1.3 meters. This is about 1.3 meters. Then what we can see here, if the velocity of the speed is constant, what happens is if the frequency increases, in this case 10 times, what happens with the wavelength is going to decrease about 10 times. Yes. Then if we analyze the equation we had, frequency, then the speed in this case is constant value. Yes. And let's see what is the relation between the wavelength and frequency. Let's divide by the frequency. Then we will have this equation. It's over frequency. And if we just apply the line test, we can see the relation between the wavelength and the frequency is inverse. Yes. If the frequency increases, this is happening here, if the frequency increases, what happens with the wavelength? The wavelength is going to decrease. If the frequency increase here is about 10 times, then what happens if the frequency increases about 10 times, the wavelength will be decreased in the same amount. Then this is why the relation between the wavelength and frequency is inversely proportional. Then if we want to graph here, yes, we will have something like that for the first one. Yes, this is the let me see if I can do a better job doing this. And this is if the wavelength is about 1.3 meters. Then what will the wavelength compared with this will be 10 times less. And we will have here about 1, 2, 3, 4, 5. Let me see if I can do a better job here, because I need to, let's see, I need to add 5 and 5. 1, 2, 3, 4, 5. Let's do the same on the other side. 1, 2, 3, 4, 5. Yes, more or less. 5. That what we can see here. What we can see here, if if you had less wavelength, the frequency will be increased. Yes, we had more frequency here. Yes, more frequency here. But if the frequency decreases, yes, we have more wavelength. Yes, in this picture we are representing the results of the last two problems. And this is all I had to discuss today.